I would like to firstly give you an outline of my presentation. I will begin with an introduction, followed by physical chemistry data and applications, the green chemistry landscape, addressing challenges and creating opportunities, collaborations, student supervision, and acknowledgements. To introduce you to my research area, I would firstly like to start with my postgraduate studies that commenced at the University of Natal in 1992, where I commenced with my BSc degree. I chose a project with Professor Trevor Letcher, and it was on activity coefficients at infinite dilution using gas-liquid chromatography. Unbeknown to me at that time, the field of thermodynamics was the perfect fit for me, because in my undergraduate studies I majored in chemistry and maths, and thermodynamics is a highly mathematical and chemical involving chemistry as well. The project that I did was a fairly theoretical study in that I investigated the adsorption of alcohols on a column using different packings. And the outcome of this investigation was that if you use low loadings on a column packing, then you would get absorption on column of the solute on the column. Subsequently, you find that most investigators always pack columns with high column loadings to prevent this adsorption effect. Once I completed my honors degree, I went on to do my master's on the same field in activity coefficients at infinite dilution, but this time I extended the study to use a range of solvents and to investigate their effectiveness for use as an extractant for the separation of closed boiling mixtures. Once I completed my master's studies, I then went on to do PhD studies, all with under the same supervisor. And when I did my PhD studies, I used a range of instruments. The first instrument is the gas-liquid chromatograph that I used. In this instrument, you have a column that has to be packed. So this is your column, and your column has to be packed by the researcher. You don't buy a column from the shelf. You as the researcher have to calculate the amount of solvent you're putting into the column, and you've got to pack it. This gas-liquid chromatograph is actually built in the laboratory. You don't use a ready-made instrument. So what we have is a water bath. Now the instrument I used was designed in this manner, where you have a water bath, and the water bath was at a temperature control that maintained the temperature of the column to plus or minus 0.1 degrees Celsius. The pressure, the flow rate have to be very carefully controlled, because all these values are used to actually calculate the thermodynamic property, which is the activity coefficient at infinite dilution. We use a chart recorder to record the retention time of a solute. That is the time it takes for the solute to elute a column. Another instrument I used was a densitometer DMA 602. This is a very, very old instrument. In this instrument, we actually use a light bulb in the water bath to control the temperature. This is not a very safe method. Now you have more modern instruments, and we don't need to use such an archaic setup. In this instrument, you measure the frequency of vibration of the solute that is found in a huge tube, and that is then related to the density of the solution by using appropriate equations. Once the density has been calculated, you then calculate thermodynamic property called the excess molar volume. I also use an LLE apparatus for the determination of solvent for the extraction of two mixtures. This is not the actual experimental setup that I used, but it's similar to the one I used. Now, in the LLE setup, what you have is that there are two solvents that have to be separated. You add a third component, and the third component will preferentially solubilize one of the two components in that mixture. And in this manner, you have two phases, and you're able to separate the one component from the other. I also use the TAM2277 calorimeter for measurement of the excess molar volume, the excess molar enthalpies. The excess molar enthalpies are actually heats of mixing that you measure for binary mixtures. Once I'd completed my PhD studies, I then went on to do postdoctoral work with Professor Trevor Letcher. And what is very important is that thermophysical data that you calculate, that you get from experimental investigations, are used to calculate the thermodynamic properties. And thermodynamic properties are used for chemical process design, and the applications of the thermodynamic properties are in solvent extraction. In this method, you have a solvent added to a binary mixture, and the solvent then will preferentially solubilize one of the components that you need to separate. In solvent extraction, you have to have calibration curves set up, so you've got to get the composition of each component that you have and relate it to a physical property, and that is what is known as a calibration curve. Because when you form the two-phase mixture, this is one phase and that's the lower one is another phase. When you form the two-phase mixture, you don't know the composition of each component that you have, of the ternary composition. So you relate the calibration curve that you have to the composition that you would get in each phase. And that is then used to determine selectivities. And if you have large selectivities, then it means that the solvent that you're using is a potential solvent for the separation of a binary mixture. The other application for thermodynamic data is in extractive distillation. Now, extractive distillation is an energy-intensive method of separating closed boiling mixtures. Closed boiling mixtures are also known as azeotropic mixtures. In solvent extraction, we do not use a lot of energy to separate a binary component. But in extractive distillation, you have to supply heat in order to separate the components. Here we have two columns. This is the first column and the second column. These are your distillation columns. So I'll give you an example. If you have your water and you have ethanol, this is an azeotropic mixture. That means this mixture cannot be separated into pure components beyond a certain percentage. So if you add your entrainer, which is the ethylene glycol, it's called an entrainer because it will selectively solubilize one of those two components. And in this example, you find that the water will solubilize into the ethylene glycol. So what happens is that the water and the ethylene glycol is found at the bottom of the distillation column, and the ethanol remains at the top of the distillation column. So by using heat, you can then distill off the ethanol and get a purer form of the ethanol. So in that way, you are separating the ethanol from the water that you have. The water ethylene glycol is then passed on to the second distillation column. And because the boiling point of water and the ethylene glycol is large, you can now separate the water from the ethylene glycol, and your ethylene glycol then remains at the bottom of the column, and it can be recycled for the next separation that you need. So that is how extractive distillation is used for separation of mixtures. So when I began my postdoctoral studies with Professor Letcher, I started working with ionic liquids. Now, ionic liquids have the potential to be green solvents. The reason why they are being classified as green solvents is because they have low volatility, they can be recycled, and they also have a range of applications. And so in this diagram that you see here, we have sigma profiles of the ionic liquids, and the sigma profiles relate to whether you have a cation or an anion. Now, that is why it's called an ionic liquid. Ionic means it's got a charge, which makes it either a cation or an anion. So here we have the negatively charged ions, and here we have the positively charged ions. Now, sigma profiles are important when you do molecular dynamic studies, and they can be used for the correlation or prediction of thermodynamic properties using CosmoRS, which is a software program. In the next slide, you can see a range of anions, but I've only shown you one type of cation. So here we have an imidazolium cation, and you can see there's a range of anions that it can be combined with. Now, because there's such a large number of possible combinations of anion and cations, which is estimated to be about 10 to the power 5, it is not possible for a researcher to do all the measurements in the laboratory. So therefore, we need to do measurements for different cations with the same anion, or different anion and the same cation, so that you can find a correlation between the structure of the cation or the anion and the thermodynamic property that you have. And this helps the computer designers, software designers, to actually predict thermodynamic properties. Here I've shown you some cations, different types of cations. You can get a pyrrolidonium cation, you can get an ammonium cation, get a phosphonium cation. So these are the different possibilities that you have. And some common anions that I use are the NTF2, which is a bis-trifluoromethyl sulfonyl anion, the PF6 anion. So there are, as you can see from these different cations and anions that I've shown you, the possibilities of the number of ionic liquids are large. Physical chemistry data and application. So where do we use the data that we get, the experimental data that we have? The physical chemistry data is actually used for the calculation of the thermodynamic properties. So the one property that we have calculated is the excess molar volumes. Here, the density of the mixture is used to calculate the excess molar volumes for binary or ternary systems. We have recently acquired a new densitometer, which is a DSA 5000M, and it's a 3-in-1 instrument that actually gives you the reading for density, speed of sound, and refractive index. We've also done measurements for binary and ternary systems. Excess molar enthalpies, I've shown you a calorimeter that I used in my PhD studies. The calorimeter is used for the calculation of the excess molar enthalpies from the physical chemistry data. Here is a photograph of the DMA 5000M. This instrument was purchased from funds received from the National Research Foundation and from DUT, and it cost about 750,000 rands. So we're hoping to get many more papers from this instrument because it is quite a highly accurate instrument. And this block that you see here is where your U-tube resides. This U-tube is where your sample is injected into, and we have PTA elements around the U-tube that maintains the temperature to plus or minus 0.001 Kelvin. So you don't need a water bath, because the first when I did my PhD, I used a very old setup where we had a water bath to maintain the temperature. So this is actually a state-of-the-art equipment, and it regulates the temperature very well. We have an automatic sampler attached to that instrument. So students, if they want to be a bit lazy, they can put 20 samples on the automatic sampler, go for their lunch, and come back, and the results will be available. But unfortunately, we also work with volatile solvents, that is solvents that evaporate, and it's not a good practice to make 20 solvents and mixtures and leave them, because the composition of the mixture will be affected. So therefore, we prefer they mix each sample and then let it run through. Then we've used the thermophysical data that we get from the GLC technique, which is the retention times. We use that to measure activity coefficients at infinite dilution. Now, activity coefficients at infinite dilution are calculated using an equation developed by Everett and Cruikshank in the 1960s. And in this method, we have to calculate selectivities. The higher the selectivity value you get, that means the solvent that you're using as the potential to be used for the separation of the azeotropic mixture. So activity coefficients at infinite dilution play a part when you want to separate close boiling mixtures. All right? And then we have excess isentropic compressibilities. These are related to the speed of sound of mixtures, and we have calculated these values for binary and ternary systems. As I mentioned before, we use the data for liquid-liquid extraction or for separation of binary mixtures. In this method, you use your solvent, and that preferentially solubilizes one of the two components. In this method, you also have to know you have to have the calibration curves, and you relate it to a physical property. The physical property we're talking about is the refractive index or the density, and your calibration curves can then be related to composition in the two phases. We've published one paper on solid-liquid equilibria, and in this method, you use a crystallization for the separation of liquid mixtures. And in this method, you don't need as much energy for the separation to take place. So what are the systems that have been studied? We've studied a range of systems from binary to ternary systems. We've done aromatic compounds with quinoline, and most of the systems that we've done were ionic liquid systems with alcohols or aromatic compounds. The systems that have the superscript here are actually ternary systems that we have studied. When you study ternary systems, you must have the data for the binary systems first, because most of the data that we have to correlate these data using appropriate equations. And these equations require the binary data. Also, having the binary data helps you to check that you have data for ternary systems that fit, have a correct fit. And you can also pick out your outliers if you check the binary data. Further systems that we have done, we've done alcohols, ionic liquid alcohols, and the methyl acetate or ethyl acetates. We've done alcohols with the ionic liquid and nitromethane, ternary systems, and many more. We've also done recently excess molar volume, speed of sound, and refractive index. These measurements were done with the new instrument, the DSA 5000M, because this instrument is a 3-in-1 instrument. It does the 3 properties for you. And we've calculated from the thermophysical data, we've actually calculated the isentropic compressibility and the change in, or the deviation in molar refraction. There are a few more systems for the excess molar volume, speed of sound, and refractive index. We get the physical chemistry data, we use the physical chemistry data to calculate the thermodynamic property, and then we also like to correlate our data with equations. And we've used the Lorentz approximation for the correlation of density using the refractive index. So experimental refractive index will be used here, and then we calculate the density. That density is then compared with the density we actually get from our experimental work. So that is how correlation would work. These equations that you see here have been used for correlation of speed of sound. So there's the speed of sound symbol there, and there's the correlation using the volumes or the density for the speed of sound. In this paper, we've actually did correlations using the graph theory for ternary system. And the ternary system was the ethyl-methyl monomethyl ether sulfate with methanol and water. If you look at this graph, you will find that the minimum of this curve lies slightly lower than -1 centimeter cube per mole at 298 Kelvin. But when you look at the higher temperatures, here we have 303, and it's slightly lower. And when you go to a 315, it is even more lower. So what does it tell you? These excess molar volumes give you information about the interaction that's taking place in this ternary mixture. If you have negative excess molar volumes, it means that you're having strong interactions between the components in the mixture. So these interactions can be because of hydrogen bonding, it can be packing effects. So when you increase the temperature, it means that this chemical interaction or physical interaction is stronger with an increase in temperature. If you look at the components in this system, we have a methanol and water system with an ether sulfate. These are systems that have strong hydrogen bonding, and you expect them to have negative VME values. In this paper here, we had published this paper using the Cibulka correlation, and in this correlation you can see that the minimum of the ternary VME lies closer to the mole fractions of your ethyl acetate and your ionic liquid. And you can see that the minimum is also becoming greater, more negative with increase in temperature. So we have a similar effect here, where we're having strong interactions between the three components that you have. In this system here, we have methanol with the negative at about -3. But this -3 is lying closer to the mole fractions of your ionic liquid and your methyl acetate. So that means your methanol concentration is very low, and you get a very low value for your excess molar volume. But when you look at the ethanol system, you can find that the negative is lying at equimolar concentrations of each of the components. So these interactions vary for different mixtures of ternary mixtures. In one of the papers we published, we used the ERAS theory for the correlation of excess molar enthalpies and excess molar volumes. This slide is for excess molar enthalpies, and here the slide is for the excess molar volumes. The ERAS theory is based on two effects. One is the physical effect, and the other is the chemical contribution. A physical contribution relates to the packing effect, and a chemical contribution relates to the intermolecular interactions that you have. So by looking at the curve that you get here, the chemical contribution is given by these dashed lines, and these are the experimental data, and that's the physical contribution. For this excess molar enthalpies, the final ERAS calculation is closer to your chemical contribution, but very different from what your experimental result is. So it doesn't describe the system as well as you would like it to. And for the excess molar volume, the ERAS equation describes the experimental data very well. So the equation works well for some systems, but not necessarily for all systems. In this paper, we have the excess isentropic compressibilities. You can get negative deviation values, and you can get positive values. The positive values indicate that the system is highly compressible. Here we've correlated some excess molar volume data using the pentic 4-parameter virial equation of states. In this correlation, you first have to correlate densities, and you can see at the low mole fraction of your alcohol, you get deviation from the actual density values. But when you have higher or mid-range composition, the equation actually correlates the data very well. Activity coefficients at infinite dilution. So, as I mentioned before, we have calculated activity coefficients at infinite dilution for a range of ionic liquids, and we also use a range of solutes for this technique. We have used alcohols, alkanes, alkenes, aromatic compounds, alkynes. So these different types of solutes that we use is actually for a particular separation problem that you're looking at. For example, if you want to separate an alcohol from an alkene, you would look at the selectivity value that you get, and if it's large, then it means that there is a possible separation. So, this table here gives you the selectivity values. The S12 infinity is actually the selectivity values, and that is your ratio of the activity coefficients of the two components you want to separate. So in this separation, we're looking at the hexane-benzene separation. So what you do is you take the ratio of the activity coefficient of hexane divided by the activity coefficient of benzene, and you calculate the selectivity value. Now, in this investigation, for the ionic liquid methyl octyl imidazolium diethylene glycol sulfate, we had a value of 10, the bottom one here. And you can see for other ionic liquids, the values are pretty high, 27, 22. So it was not a very good ionic liquid for this separation. But if you look at the next slide, where we did the PF6 minus ionic liquid, this ionic liquid, we had a much better selectivity value. And if you compare it with NMP, which is the normal solvent that is used for this separation, it is higher than that. So it seems like a better solvent for the separation. But sulfolane is the common solvent that is used for the separation, and sulfolane has a very high value. So it is better than NMP, but not as good as sulfolane. The figure at the bottom here, this figure here relates to the ln of the activity coefficient versus 1 over temperature. This plot is done to calculate the excess molar enthalpies at infinite dilution. So this will give you, if you have slopes that are positive, you tend to get excess molar enthalpies that are endothermic, but if the slope is negative, you get exothermic excess molar enthalpies. From the excess molar enthalpies, you can calculate the Gibbs excess function. In this paper here that we published for the hexane-benzene separation, we had values for the separation that was 37.5. So there's your ionic liquids, your ethyl, methyl, imidazolium, plus trifluoromethyl sulfonide imide. You got a high value here compared to the previous selectivities, higher than sulfolane. So this was a very good ionic liquid for this separation. And in the next paper, we've published data for the same separation for the octyl ammonium ionic liquid. And you can see that the selectivity for this is very low, 3.5, so it was not very good. So we do this calculation for different types of cations and anions so that you can develop a program that can say, for a particular separation, this anion and this cation combination gives you the most suitable solvent to use. Liquid-liquid equilibrium studies were done for a range of ionic liquids and for a range of separation problems. In this separation problem, you've got a benzene and an alkane. Here you've got benzene with hexadecane and heptane. And here you've got an alcohol and an alkane. So you're looking at separation, and then you've got your solvent that you're adding there to try and do the separation and get your selectivity values. This is the quinoline alkanol plus water system. You can see that the ternary phase diagram gave you a very small, this is known as a two-phase region, and that is known as a one-phase region. And here you have tie lines. The tie lines in the two-phase region actually is used for the calculation of selectivities. For this system, we didn't get very high selectivity values. In fact, the highest one was for the 1-butanol water separation using quinoline. And in the next system that we studied, which was the ionic liquid and alkane and aromatic compound, we have a bigger two-phase region, and the selectivity values for that separation for the aromatic compound and the alkane range from between 36 and 12. And if you look at your NMP, which is the solvent that is used normally, you can see that NMP tends to have higher values. So that didn't give us a very suitable ionic liquid for this separation. Where do you use the physical chemistry data and the thermodynamic data? You would use it for process design for industrial separations. You will use it to select your solvent for extractive distillation. You would use it for selecting the solvent for solvent extraction problems, and also for the development of new models for the correlation or prediction of your thermal physical properties. Now come to green chemistry. So the question is, how is all this physical chemistry data now going to be related to green chemistry? Firstly, I'd like to give you the background, a small background on green chemistry. In 1997, the Kyoto Protocol was signed by 192 countries, where they declared the intention to reduce the greenhouse gas emissions that contributed to global warming. It was found that the atmospheric temperatures had risen by about 0.8 degrees Celsius in the 20th century, most of this since 1980. And also, if no reduction in the greenhouse gases was taken, then you'll find that the temperatures of the atmosphere at least would increase by 1.1 degrees Celsius to 2.9 degrees Celsius. And if you and the maximum increase was predicted to be about 2.4 to 6.4 degrees Celsius. So these are very large increase in temperature. So if we don't decrease the emission of the global greenhouse gases, then you're going to get melting of the ice caps, and there was steps put in place to try and reduce the emission of the greenhouse gases. And in 1998, Paul Anastas and John Warner published the paper Green Chemistry Theory and Practice, which was published by Oxford University Press. And in that paper, they outlined 12 key principles for green chemistry. And they said that you've got to use chemicals that can be recycled, you've got to use chemicals that can minimize the use of chemicals. You've got to use non-volatile chemicals. You've got to also use renewable sources when you're doing your process design. Okay, so you've got to look at renewable resources for chemical reactions. So, what is the link between the physical chemistry and green chemistry? At face value, there's no direct link, but when any new process is developed, you need to know the thermophysical properties and the thermodynamic properties. So, it was stated that ionic liquids, which I have studied since my postdoc, it has the potential to be used as a green solvent. So, as a developing researcher and a young researcher, I was looking at opportunities to use ionic liquids for a green chemistry application. And the first thing that comes to mind is that you've got to collaborate if you want to build yourself and you want to develop and grow. So when I did my thermodynamic data, I collaborated with many people so that I could get use of equipment, I could get correlation of my experimental data. That is classified as sort of fundamental research. But if you want to go on to green chemistry, then you've got to do something that actually it extends that knowledge. So the question is, what are your challenges and what opportunities can be created? So firstly, we find that in society we have high unemployment, we've got crude oil stocks being depleted, fuel prices increasing, and of course your global warming effects, which is leading to high temperatures. And of course, sustainability. You have to design new chemical processes that speaks to sustainability, okay? So, while reading papers on my work, thermodynamic data, I've also read papers that spoke about the use of ionic liquids for green chemical processes, and stated that ionic liquids can be used as green solvents. So, how is ionic liquids used as green solvent? It is used as a reaction media for organic syntheses. It is used for solar cell technology because it has a high thermal stability. It is also used as rocket fuel. And when I saw this pre-treatment of lignocellulosic material, it sounded something very interesting. And when I talk about my collaborations, you will see how this idea unfolds. Now, when you look at lignocellulosic material, it is one of the largest sources of cellulose, a natural resource, and it is something that is a sustainable resource. Okay, you can keep planting these lignocellulosic material, and you won't have a problem with the bioresource, the source of it. So, lignocellulosic material contains lignin, hemicellulose, and cellulose. So lignin is on the outer coating of this biomass. Your hemicellulose is between the lignin, and your cellulose is actually within this framework. So if you want to use the cellulose for value-added chemicals, you have to remove the bonding between the lignin and the hemicellulose so that you can access the cellulose that you have in this biomass. It is not easy, and that is why you find that it's difficult to take these cellulose and convert it to value-added chemicals, bioplastics, biofuels. And many papers have been published on the use of ionic liquids for pre-treatment of lignocellulosic material. So what does pre-treatment mean? It means that when you react the ionic liquid and your lignocellulosic material, it actually loosens the bonds between these three components in the biomass, and you can then access the cellulose that you have within the structure and convert it by different methods to your end value chemicals or your bioplastics or your bioethanol. Collaborations. Firstly, in my physical chemistry data acquisition and thermodynamic studies, I collaborated with the University of UKZN, with the Warsaw University of Technology in Poland, with the California State Polytechnic University, and with Professor Martin Eisner from the University of Campinas in Brazil. And this was for purely the thermodynamic correlations. Recently, my GTech student, Ms. Zikona Twabi, was given an NRF apprenticeship with the CSIR in Pretoria, and if people know me very well, they would know that I'm very close to my family, and they wouldn't like me to be traveling to Joburg every weekend to supervise my student. So fortunately for me, she was transferred to Durban, and she got a position at the Forestry and Forestry Products Division of CSIR in Durban, working with Dr. Bruce Sitole. So she was looking at the regeneration of dissolved pulp using ionic liquid. And she had went to the States about a month ago, and she spent 2 months, she went about 2 months ago, spent 2 months there working with Professor Robin Rogers, who is a world leader in this field, and she's done some experimental work. So I am waiting patiently for her to write that paper, give me the draft, and so we can have an output from this research experience that she had. And that was the one collaboration that came out because of the NRF funding that she got. And the second potential collaboration was with the Sugar Milling Research Institute. My good friend Prashant Reddy, who's sitting in the audience, he was a honors student when I was at UKZN doing my PhD studies, or was my postdoc, I can't remember, it's been a long time for me. And he recently got appointed at SMRI for the for the investigation of ionic liquids for sugarcane bagasse treatment. And he approached his supervisor, Dr. Steve Davis, and asked him if he would be interested in a collaboration with us in DUT. And Dr. Steve Davis was very happy about such an initiative, and we have agreed that we will do some collaborations together. So I have a student, Ms. Tandeka Nkeys, who just registered for the Masters, and she will be doing this project on the pre-treatment of sugarcane bagasse using ionic liquids. And the purpose of this investigation is to see if we can unlock value from the cellulose that is found in sugarcane bagasse. Because sugarcane bagasse at the moment, or currently, is used as a fuel in the milling, in the sugar mills. And if you can convert it into value-added chemicals, then obviously you get more value for your money, so to speak. I also have two BTech students are doing some preliminary investigations on lignocellulose pretreatment and their possible conversion to sugars. Prof. Bauer has alluded to this earlier about forming international relations, and what we've done recently is we put in an IPSA proposal for funding, and I'm hoping that comes through. So here we have the South African component of the application. We have some new potential collaborators from India, Professor Varma and Professor Coulthard. They are well published in this area for the pre-treatment of lignocellulose material and their conversion to value-added chemicals. And then Prof. Martin Elsner, I know from my previous collaboration with him, and I actually visited them in 2012, and I presented a paper at the University of Campinas, and his wife is Professor Aline Carvalho da Costa. And it so happens that his wife is as doing research on sugarcane bagasse pre-treatment with ionic liquids and the kinetic study of it. So, as being an opportunist, I decided to approach her and ask her if she would like to be the Brazilian component of the IPSA application, and she was quite happy to do so. So hopefully, if the funding comes through from there, then I won't be seeing Prof. Moyo and Prof. Oceano and asking them, please can I have some funds? I've got no funds to do my research. And then I have my stupid, sorry. Then I have student supervision. I've supervised a number of masters, doctors, research assistants, and honors students, and some of them are in the audience, some are still with me, and some of them have gone into greener pastures, I hope. And without my students, I wouldn't have done all that work that I did. I've graduated a few students recently. I'm hoping to graduate a few more students. Acknowledgements. I would like to acknowledge my supervisor, Professor Trevor Letcher, who was at the right place at the right time for me, because I actually enjoy thermodynamics. I like the chemistry part of it and the mathematical part of it. The National Research Foundation for funding, for my Tutuka funding for 6 years, for my conference funding, for my bursaries for my students, the Durban University of Technology for funding for equipment and student bursaries, and my collaborators, my postgraduate students. Without my postgraduate students, I wouldn't be able to have published and have such a number of publications. And finally, the Higher Education South Africa for the IPSA funding for the IPSA workshop that I hosted. I think it was 2 years ago. And most of all, I'd like to say thank you to all of you for taking time out of your busy schedule and spending it here with me this evening. Thanks.